didn't collapse now are able to collapse, right? So we know that these stars were just born. Here's why. Some of these stars are so big that they only last 100 million years. Now I'm speaking very strangely here. Wouldn't you think a big star would last a long time? But that's not true. Giant stars burn their fuel up. It's kind of like the tortoise and the hare, you know, kind of a thing, right? They burn up their fuel much, much faster, okay? And so giant stars don't live long. And we know they're giant by their color, right? It's easy. We can look at them. They're blue. Big blue stars are brief. Yes? Right. There's tons more gravity. And so it's, I believe they consume their fuel at a rate proportional to their mass cubed, right? Their mass cubed. So if they burned it proportional to their mass, they'd last longer, right? But they burn it proportional to their mass cubed, roughly. Yeah.
So, but then why is, because I know that like our star isn't the thing that in millions of years when it dies, will be slowly turn into a red giant?
Yeah.
So why is these stars so pure blue? Are they?
Oh, they're blue because they haven't done the red giant thing. In fact, they might skip all that. They could just do, you know, they burn out really fast and go boom, right? Yeah. I don't know that they'd actually do a, I mean, supergiant stars are strange, right?
Stars are bigger than red giants or red stars?
Well, they may never go through the red giant thing, right? They might just collapse, boom, you know. I mean, they're basically, if you could see this in any galactic sort of time frame, these guys would be like little sparks in a fire, right? They'd be little things that go crackle pop, right? You know. Whereas our star is going to last 15 billion years, right? The tiniest ones on the main sequence last hundreds of billions of years. This is a little gallery of galactic collisions. They're ultraluminous infrared, but they're also luminous in any wavelength. They're bright because they've a bunch of new stars have been born. Here's Andromeda, is a spiral galaxy, right? It's kind of a cow pie, right? These are a couple of elliptical, miniature elliptical galaxies that are orbiting Andromeda. So galaxies orbit other galaxies. And in fact, this little miniature group of galaxies actually orbits us, or we orbit it. Yeah? Kind of a thing, right? And in fact, we have our own little mini-me's orbiting us. Who is drumming? Thank you. Okay, so we have our own little miniature ones. They're called the Large and Small Magellanic Clouds. Okay, they were discovered by
Magellan.
Yes, there we go. And they're only visible in the southern hemisphere.
Magellan?
What? Not the navigational instrument. Okay. No, maybe I don't know. What's the right answer? There are 10 to the 11th galaxies in the visible universe. So this is easy to remember. About 100 billion stars in our own galaxy, 100 billion galaxies in the visible universe, right? And the closest one is about 2 million light years from us. And this is called the Hubble Deep Field. Basically, they looked at a spot in our sky where there aren't many stars, or as few stars as they could. They pointed the Hubble telescope at that spot for days, right? Of course, it goes behind the Earth every now and then, right? It orbits the Earth, right? So they just pointed it at that spot night after night after night after night, okay? And every little dot here is a distant galaxy, and there's lots of them. And then this is a star cluster. These things are found in galaxies. These are much smaller. These are thousands of stars. Okay, some of them are interesting. There's something called a globular cluster. Globular clusters, we think the stars are all the same age, right? So it's kind of as if a bit of star material went puff out into space and all condensed at roughly the same time. Kind of like if you breathe on a cold day and go, you make a little cloud of condensation. Those are little droplets, right? Imagine them all stars. Okay, these are important as far as stellar evolution. We use these things to predict the path that stars take. And then now we're going to talk about nebula. These are small things inside galaxies, right? So I'm not talking about spiral nebulas, which are really galaxies, or elliptical nebulas, right? We're talking about real nebulas that are still called nebulas, okay? They're clouds of dust and gas, and they're categorized not by what they are, but the way they look. Do I like that very much? Not so much, you know, but there they are. An emission nebula is one that's emitting light of a different color. So it's rebroadcasting. It's kind of like black lights shine on stuff and then the stuff glows. You ever seen that? Yeah. Like black light posters and stuff like that. This is super giant stars like that one there are emitting ultraviolet and ultraviolet radiation, like super high frequency, low wavelength. And that radiation is making the gas around the star glow, just like a fluorescent light bulb. And the green is like, I believe, nitrogen, and the red might be hydrogen or something like that. But they correspond to particular spectral lines, right? And then reflection nebula, this might be made of the same stuff that that one's made of, but it's called a reflection nebula because the light's shining, just like light on snow, you know? Okay, so there's a bright star shining on the sky, and it looks like a reflection nebula. That's just the way it looks, yeah? Now, notice how this stuff, when we looked at that picture, and I'll show you a better picture of it, didn't it look like it was all falling like a waterfall? It looked like a snapshot of Multnomah Falls. The reason for that is that the radiation pressure of the star that's shining its light on this is blasting that nebula away, yeah? All the charged particles, all the photons from it are blasting it away. This is called the Horsehead Nebula. It could be made of the same stuff as this guy, but it's called an absorption nebula because it's absorbing the light from a distant emission nebula. Do you like that? No. Yeah, so things that just block the light are called absorption nebula. Hopefully they won't quiz us too heavily on this, right? Right. The only thing that deserves to be called a different thing and is really different are planetary nebula. Right? These should be called something else, okay? But planetary nebula are actually the result of those bipolar jets. Somebody I think in here was talking about the bipolar jets. Dying stars can get jets of material that shoot off of either end. And this one here, the Hourglass Nebula, is actually probably has a shape like this. Okay? And we're actually looking at it like this. What's making this nebula is that there's a dying star in here that's ejecting material this way and this way at the same time. And it's probably precessing because it's orbiting something else. And so it's going like this, spinning like an unstable top, right? It spins around and is shooting stuff off into space. These things are totally cool and totally different from these. These are just clouds of stuff left behind where planets or solar systems might get born, stars and solar systems.
Wait, Murray.
Yeah.
Why would a planetary nebula do that? Why would it spit off star material?
When it becomes like a white dwarf, right? It actually it creates a magnetic field. We're not exactly sure how the bipolar jets are created, but we think its magnetic fields channel it, and it just shoots it off into space. Yeah.
I don't know. Don't normally when stars die, they either get too massive and they explode.
Yeah. This one hasn't exploded yet. It's still too hot. These are white dwarfs, right? So they're still doing like carbon fusion, right? They're super, super hot, but they are pretty dense, right? And they're shooting stuff off into space.
You just think that shooting stuff off into space would break up the equilibrium, and then all of a sudden one of those forces would win.
Yeah. Eventually it's going to cool down, and then it's going to, if it's big enough, right? I'm not sure that that's the exact trajectory of these guys, but here's some bigger pictures. This is our emission spectrum, and this is the one. Now you can't see, if you looked in a telescope and looked at this, it would just look like white light, okay? This is not false color. Basically, you can't see color at low light levels. I don't know if you've noticed that, but when the light gets really, really dim, you can't see color very well, right? And that's because the cones in your eye are not very sensitive to light, but the rods are or something. Rods are black and white, cones are color. So these pictures this is real color, but you have to do like a 15-minute exposure or something to see that. Okay, these are those gaseous pillars again. See how it looks like the stuff is all falling like this? Of course there's not gravity, it's not falling, right? What it is the star that's above there, that's shining its light on there, is also the light is exerting a pressure, okay? So it's breaking up these nebulas like that. Here is our absorption nebula. The North America nebula is also looks like it's an absorption nebula. It looks like North America. Right? What kind of nebula is this? This is planetary. This is a totally different thing, totally different phenomenon. Okay? These things have what's called point symmetry. It's a different kind of symmetry. It's not bilateral symmetry. It's not circular symmetry, anything like that. Point symmetry is a point here has an equivalent point there. So here's the most notable point there, right? It's spewing stuff here, it spews stuff there. When it tends to spew stuff, it spews it out of both ends. Have you ever felt that way? Yeah, there we go. Don't you hate that? How many people have been that way, right? You don't know whether to sit down or kneel. You're so sick, right?